First, I would like to begin with planetary circulation patterns. For example, seeing the atmosphere through the clouds. This is an Earth model visualization from NASA showing clouds from a simulation using the GEOS model version 5. Most days, the atmosphere is transparent and difficult to see with the naked eye. Occasionally, though, clouds, dust, fog, or smoke allow us to see the movement of the air around us. Also, clouds help us to better see and understand the atmosphere. From this simulation, we can answer questions like, where are the clouds? Why do they move? Are there areas where without clouds? Are there areas of extreme clouds? Do the clouds move east and west, north and south? What other patterns of motion do you observe? And how do clouds allow us to see the wind? Next, I would like to get into the scales of weather and climate. The atmosphere is one interconnected system. For convenience of study, scientists subdivide the atmospheric circulation and weather patterns into categories based on their size and duration. In general, the smaller local scale weather events have the shortest life expectancy, while the global scale patterns can persist for weeks or months.
Atmospheric flow, also known as atmospheric circulation, is caused by the sun heating the Earth more along the equator than at the poles. As warm air at the poles rises, it circulates and flows towards the poles. As it gets towards the poles, it cools down and descends to the Earth's surface, where it flows back to the equator, and the pattern repeats itself. The Earth's rotation also affects atmospheric circulation. Air flowing to the north rotates to the right, and air flowing to the south rotates to the left. This is known as the Coriolis effect, and these are the reasons why we have trade winds. If the Earth did not rotate in space, there would only be two major convection cells, that north and south of the equator. But because the Earth does rotate in space, this causes several different air circulation cells.
Earth's atmospheric flow is generally separated into three cells, the Hadley, Ferrel, and polar cells. The Hadley cell extends 30 degrees from the equator and contains the northeasterly trades. From 30 to 60 degrees is the Ferrel cell, containing the westerlies, and the polar cell sits above all and contains the polar easterlies. The cell wind direction comes from the atmosphere receiving a force from the rotating Earth perpendicular to its axis of rotation, commonly referred to as the Coriolis effect.
So actually how we're going to figure out how to find the atmospheric flow is based on one of the four factors, which is going to be buoyancy. We're not going to look at pressure gradient. We're not going to look at rotation, but buoyancy. And buoyancy comes from turbulence, because turbulence is generated by the heat of the air on the surface, which is this convection process, which is a three-dimensional process. And we have free convection, which is based on the thermal rising, which is based on the temperature gradient, which is a buoyancy convective. And that's what we're going to focus on. Instead of looking at the forced convection, which is a mechanical wind shear, and also the mixed convection, which is both of these. And so based on this, we can actually find how fast you can actually get the atmospheric flow going, which is 3 meters per second. And this is based by the air buoyancy parameter, which is the gravity, the acceleration of the Earth, represented as g, and underneath that is divided by the virtual potential temperature, which is virtual potential temperature is a measure of the humidity in the atmosphere. And because we're dealing with heat, we can focus and figure out this problem. So when we actually take that buoyancy flux, we can relate that to W star, and W star is what we're doing as our free convection scaling to find this. And this is also dictated by the altitude or height in the atmosphere.
The atmosphere flows are results of the atmosphere pressure, gradient force, friction, and rotation force, so the Coriolis force, and the pressure difference is one of the most important point. And in the conclusion, based on our research, the jet stream can move up to 247 mph, and that is the fast flows based on our research. Thank you.